Hello, everyone. Yes, I'm Prasanth Peddaayyavarla. I'm head of data science in advanced analytics unit in Finance Institute. Today we are going to talk about predicting admissions due to severe exacerbation and patient people diagnosed with COPD. Let my colleague Kamil please.
Hello, I'm Kamil. I work with the data science team as well. Yeah.
Okay. So this is a machine learning dashboard project that is part of our R&D pipeline. So what we wanted to do was give a solution to clinicians or GPs and nurses to be able to have a tool that could stratify the patient to your risk of having COPD. So I want to talk a little bit about COPD. Probably know most of it, but I'm going to just quickly intro it. So COPD is a heterogeneous condition. Patients have different kinds of symptoms, different phenotypes, and they have. It's not necessary that every patient has the same set of symptoms. And it's a deteriorating condition, often diagnosed late. So it's highly important to diagnose it early, even though it's too specific for diagnosing. But catching, doing interventions early on is very, very important. I want to refer to one of the Canadian studies that tracked patients for 17 years, COPD patients, and there are some very, very useful insights from that study. So one of the things that they found out is that they've done a survival analysis, and they found out that every severe exacerbation increases the risk of the next severe exacerbation. As you can see from our data set itself, or what we use in our data set, the median number of days between first and second admission is 176 days. Third is second, third is 104, and as you can see that as the disease progresses, days get clustered. That means the risk increases. So it's very important for us to intervene at the right time. The same study said that if we intervene before the second severe exacerbation because of admission, that's the I don't want to say the sweet spot, but that's the time to intervene, the right time to intervene. We want to give our GPs that kind of information. Say this patient had one admission, and last 6 months back, or this is where we need to intervene if they were going to mention this. So just to talk about a little bit about trends after COVID, the rate of admissions dropped, but still they are in a slight increasing trend. Still beating there is a gap, and especially in terms of preventive care. And as you can see that a new discipline. So the objective of the machine learning model here is we wanted to predict the next exacerbation for a patient based on the clinical, non-clinical data. We trained the model, we deployed the model, and we have basic predictions on it. So just to don't dwell too much on this, but this is our pipeline for machine learning models. So as you may have heard already many times, the data extraction takes the longest, and every time we extract the data, we try and repurpose it for other use cases. We train the models, several models, traditional as well as black box models, but we always weigh the performance versus simplicity in terms of deployment, simplicity in terms of information when it comes to sometimes for this model, you can deploy this server without needing any forms. In this case, we have deployed it on the Azure platform on the endpoint, with flags in the real time, and because in the next step to streamline the stuff. In terms of the feature engineering process, we started with 123 variables, looking into the literature search, looking into speaking to our in-house clinicians, and speaking to your analytical experts. We looked into documentation like gold. So we came with 123 potential variables. Put through our process of data collection. And finally, we boiled out that to 29 variables. The variables span between whether it's secondary categorization or primary categorization, community categorization, the comorbidities, the medications, the test, like the score or the assessment like MRC. So as with any machine learning models, you train them to train and validation set. So that all the results that we see are based on that. So to give a context of our cohort, were 16,750 patients with a stratified state of 7.25. And out of that, a very small percentage got I think it's sort of 6% got in a year. So therefore it's quite an imbalanced problem. So when we train the model, only specifically for training, we show that data because it's an imbalanced problem. What that data gives is it gives you an opportunity to tweak your model so that you capture most people who are at risk of admission, even though you have no false positives. So we can compromise on false positives, therefore we don't miss the patient. So that was our main intention. We should get use a beta 2.5, tweak that, tune that, and use the best possible model. Pass on to Kamil to see our results.
So as my colleague was saying, so F data is one way to assess the performance of the model, but there's a number of different ways as well of doing that. So one way is a visual way. So this is a visual way of assessing how the model is performing. And I'm not going to go into sort of very specific details of how this particular graph is plotted, but it's a very well-known graph. It's called ROC curve. And what it basically tells you is gives you a balance between sort of your model's ability to detect the true positive cases over the false positive cases. So basically, as you sort of reduce the threshold of detection for your model, so for example, you can set that, if the model is telling me that the probability of this particular case being a true positive case is 10%, I could have a low threshold to say that, okay, if it's 10% or more, I'm going to say this is going to be a true positive case. So as you kind of vary that threshold, the ratio between your ability to detect the true positive cases and the false positive cases changes. And what you want is that ratio to be higher, basically. So if you look at this curve, and sort of the higher up the curve is to the left, and that left corner, the greater that ratio is, and so the better in terms of your model's ability to distinguish the positive cases that you want. So yeah, so I can answer more questions about that if somebody wants to. Let's so here, so this is sort of digging down a little bit more and showing a bit more about the model itself. So on this side, what you'll find is that any kind of given model, obviously repeated a lot of variables. So Prasanth mentioned the variables that were collected. So this is a list of some of those variables. And basically, for any given model to make its prediction, it has to kind of associate a coefficient, sort of a level of importance with each of those features. And so here are the sort of relative coefficients with some of the features. So for example, on the very top, you will find days since the last emergency admission. So that is, for example, our most predicted feature out of the ones that we were able to collect in terms of giving us information that this person is likely to be admitted again, which kind of makes sense. And a few other features out there as well, things like prescription, like total number of prescriptions that the person is taking out, and things like that. Here on this map, so we kind of isolated one variable just to kind of have a look. So we're using something called the SHAP score. So the SHAP score basically is just it gives you a sort of an indication of sort of the influence that a particular feature has on a one given prediction. If you take one patient, the SHAP score will give you sort of an indication that a given feature, how much of an influence basically that feature has on the prediction of them, for example, being admitted to the hospital. That means a positive prediction for them being admitted to the hospital. So here we're looking at BMI being our feature of interest. So you can see that, for example, you can see that the BMI sort of for a particular, so these are all different people. So for a given person, for example, you will see that for a given BMI, it might reduce or increase basically the chance of being admitted, but it depends on that particular value, and the SHAP score gives us that indication. So this is just looking at one individual case, and this is kind of where the SHAP score becomes very interesting, because a lot of the times, when you look at a model, you can look at all the different features and how they sort of affect the whole population, but here we can actually look at the individual patient, and so you can see when you isolate that patient, it can tell you basically, this is the information that we've got for the patient, and it tells us, okay, for that information that we've got, what sort of influence do those features have in terms of predicting them to being admitted. So this person, the SHAP score of 0.86 is the probability of them being admitted to the hospital. And we can see that there's a lot of features that increase that probability, that push that probability to go up to 86% instead of it being, for example, 0, right? So you have a lot of features like, again, so for this person, they were admitted with COPD once in the past, and that has pushed the probability to be pretty high. And a few other features as well, again, like utilization and other admissions and things like that. For this particular patient, the fact that they have a high BMI actually had a negative influence in terms of like reducing the probability of them being admitted, and there's a nutrient sort of relationship there for that particular patient, but it is for that particular patient, but we can't really generalize from that. For this patient, this is how BMI influences influence the probability. And this is just another patient as well, again, looking at a different relationship. So here, for example, the probability of the patient is low, and that's because they have a lot of features that tend to reduce their probability of being admitted. So, for example, things like age, then being 61, that reduces the probability of being admitted, because people that are older than that would be pushed towards being admitted, and other things as well. So, on balance, you can see that they have a lot more features that kind of influence them and prevent them from being admitted, basically. So you have a lower probability of 0.26. And yeah, so the final model, so the model that we've developed, it is functional and it's already deployed, so it's not used by any client as such, but it already exists in our platform on Azure, and so it can be used in a number of different ways. And you can, for example, input the features that of a particular patient to get a prediction, to see basically what the probability of the prediction will be. You can do it in a batch, so you can input a bunch of patients, a whole list of patients with the feature, and then given feeding a table, giving and receiving a table back. And that can be saved to a SQL server that anyone in your organization could access. So we it's very functional and very accessible once deployed.